Welcome to this explainer. Chemistry math can often look pretty intimidating. If you've ever stared at a chemical equation and felt like you were trying to decipher some ancient foreign language, trust me, you are not alone. But today, we're going to transform that dry math into a genuinely engaging puzzle-solving experience. By mastering what's known as the hit and trial method, you're going to see exactly how these molecular puzzles click perfectly into place. Keep this classic brass balance scale in your mind's eye for a second, because it really anchors everything we're talking about today. That scale, it represents the universe's absolute demand for equilibrium. Basically, in chemistry, what goes in must come out. There is absolutely no cheating the scales of nature.
And this brilliant concept is formally known as the law of conservation of mass. It is the unbreakable rule of physics. Think about it like this. If atoms seem to just vanish into thin air or suddenly appear out of nowhere in an equation, a scientific crime has been committed, and it's our job to investigate and correct that crime.
So here's our roadmap for today. First, we'll quickly cover the law of conservation. Then, we'll look at skeletal versus balanced equations, dive deep into the hit and trial method, solve a chemical puzzle together, and finally wrap up with some golden rules. By the end of this explainer, you're going to be a master chemical detective.
All right. Section 1. The Law of Conservation. Let's establish the real stakes of our investigation.
So when you see a chemical reaction that lacks balance, it literally means the fundamental rule of the universe is being ignored. As we learned from the brilliant mind of Antoine Lavoisier, matter cannot just disappear. Even if a substance is undergoing a massive change, like combustion or rusting, every single atom has to be accounted for. When an equation doesn't reflect that reality, we have to step in and fix it. Moving on to Section 2, Skeletal v. Balanced Equations. Let's meet the actual culprit hiding our missing mass.
A skeletal equation is essentially the villain here. It tells us what happened, like methane and oxygen reacted to make carbon dioxide and water, but it hides how the mass was conserved. It completely leaves out the quantities. A balanced equation, on the other hand, restores order. It equalizes the atoms by adding those crucial big numbers in front, which we call coefficients.
And this brilliantly illustrates why this matters way outside the pages of a textbook. If you rely on skeletal equations in a real-world laboratory, your stoichiometric ratios, the precise chemical recipes, are going to be entirely wrong. You might mix the wrong amounts, which could lead to physical danger, like an unexpected explosion, or just a massive waste of really expensive chemicals. Accuracy is quite literally a matter of safety. Section 3, the hit and trial method. Let's see how this builds into our primary investigative tool.
The key here is following these exact methodological steps to logically restore balance so you don't get completely lost in the numbers. First, you just write down the bare bones. Second, take inventory. Count every single atom on the left and the right. Third, add coefficients to balance just one element at a time. Fourth, and this is a major pro tip, always leave hydrogen and oxygen for last. Why? Because they tend to pop up in multiple different molecules, so balancing them too early will constantly throw off your other numbers. And finally, just verify the count.
Section 4. Solving a chemical puzzle. It's time to walk through a live crime scene and actually put this hit and trial method to the test. Let's get our hands dirty.
Okay, here's our scene. The raw, unbalanced reaction for burning methane. We've got our reactants going in, CH4 and O2, and our products coming out, CO2 and H2O. At first glance, our hydrogen and oxygen suspects are definitely mismatched. Setting up this suspect tracking table makes the crime blatantly obvious. Look at carbon. Totally innocent. One going in, one coming out. But move down to hydrogen. We have 4 atoms entering the reaction, but only 2 coming out. And oxygen? A total mess. 2 going in, and a really bizarre 3 coming out. Let's apply step 3 of our method. Using the hit and trial method, we know we need more hydrogen on the product side. Now, this isn't random guesswork. It's an iterative, logical strategy. We hit upon an idea and trial it. We obviously can't change the water molecule itself, but we can say we produced 2 water molecules. So we place a coefficient of 2 in front of the H2O. Boom, that successfully balances our hydrogen atoms to 4 on both sides. But how did this affect the rest of the scene? Let's recount. Carbon is still good. Hydrogen is fixed at 4 and 4. But here's the one step forward, one step back nature of this method. Our adjustment means we now have 4 oxygen atoms on the product side, 2 from the CO2 and 2 from our new water molecules. Compare that to just 2 on the reactant side. So now we have to go back and fix the left side. To close the case, we just trial another hit. We multiply the reactant oxygen molecule by 2. This gives us a beautifully updated equation. CH4 plus 2O2 yields CO2 plus 2H2O.
One final look at our table verifies that every single atom is accounted for. We've got 1 carbon, 4 hydrogens, and 4 oxygens perfectly mirrored on both sides. The puzzle is solved, and the universe is safely restored to equilibrium.
Finally, Section 5, Golden Rules to Remember. Before you tackle these puzzles on your own, we really need to review some common pitfalls.
Getting the hang of this requires adhering to a few strict boundaries. First, always start with your largest, most complex molecule to anchor the equation. Second, keep polyatomic ions, like a sulfate group, SO4, grouped together as one unit if they don't break apart during the reaction. It literally saves so much time. Always double-check your final count. And above all else,
I seriously cannot stress this enough. Never, ever touch those tiny subscript numbers. If you alter a subscript formula just to make the math work, you aren't just breaking a math rule, you're magically transforming the substance into something completely different. For example, changing H2O to H2O2 to balance oxygen, that turns safe drinking water into hydrogen peroxide, a toxic chemical. You've ruined the reaction entirely. You can only change the big coefficients in front.
I want to leave you with this final, high-stakes question to ponder. We've been looking at numbers on a screen today, but imagine the very real and sometimes explosive consequences of forgetting the law of conservation of mass when dealing with thousands of gallons of volatile reactants in a massive industrial plant. The hidden trial method isn't just some trick to pass a chemistry test, it's the fundamental language of reality, keeping our world safe, balanced, and deeply fascinating. Thanks for joining me on this explainer, and keep solving those puzzles.